All right, welcome everybody to today's seminar in Physics Meets ML. We are very happy to have Alejandro Ribeiro from UPenn. Alejandro did his undergrad in electrical engineering in Uruguay. He then went on for his graduate studies to University of Minnesota, and afterwards he joined as a professor at UPenn. His research interests are in the application of statistical signal processing to collaborative intelligent systems, and more specifically, his interests are in wireless autonomous networks, machine learning on network data, and distributed collaborative learning. Alejandro has received numerous awards, including paper awards at ICASP and UCIPCO, and he has also received several teaching awards. So it is our great pleasure to have him. He will talk about algebraic neural networks, stability to deformations, and if you have questions, please feel free to either interrupt him, post them in the chat, or ask him at the end of the talk. So with that, I hand over to Alejandro. Please go ahead.
Yep. So thanks a lot, Fabian, for the introduction. Thanks a lot for the invitation, and thanks for all those of you that are in attendance, in sync or out of sync. So as Fabian said, the title of this talk is going to be about algebraic neural networks, and in particularly, I will talk about stability to deformations of these information processing architectures. This is joint work with my postdoc, Alejandro Parada Mayorga. The reason his name is in red here is because I am giving the talk, but you should remember that he deserves equal credit for this. If you need to reach me, this is my email, this is my lab's website. Let me begin with an introduction here, and let me begin with an introduction at what is perhaps an excessively basic level, but just so we are all on the same page. The idea of machine learning, I think it's pretty simple. Or we can all agree that the idea is to move from signals or data to information. So we're given some input data and we want to extract some information of interest. So these images are made up of individual pixels, colors, and luminance. That's our input. And we know that this represents the Eiffel Tower. That's our information of interest. Another example, which as Fabian was reading my bio, this is goes to the core of the things that I care about in my research. We have here a team of drones which they want to coordinate their velocity. So here, each of the drones senses their own velocity. They measure distances to neighboring drones, and out of that information, they want to determine accelerations that would lead them to coordinate their velocities globally. Right? So the challenge here is that you are seeing local observations only, but you are trying to get global behavior to emerge. Now, central to any of these machine learning problems is the notion of the learning parameterization, right? Because the machine learning problem, mathematically at least, has a very simple definition. Given input-output pairs in a training sets, we want to find an approximation, a function approximation that generalizes well. Now, in order to do that, the notion of the parameterization is crucial, right? So the parameterization is what controls how we generalize well. And the idea of the parameterization is to restrict the space of allowable maps over which you are searching for this function approximator. For example, you could suggest that we are going to approximate, or that the input-output map is going to be represented by a linear function. Perhaps more interestingly, you add a nonlinearity at the output of your linear transformation. That's what you would call a perceptron, and then you try to find an edge within this class that approximates your data as best as possible. Now we are, of course, in the year 2020, right? And in the year 2020, the architecture that has proven to be successful beyond expectations is that of a neural network. Now, a neural network is not that different from a linear transform, and I think that that's important to recognize, because what you do is you get these individual linear transforms and you apply pointwise nonlinearity to them. After applying this pointwise nonlinearity, that defines layer one. You go into a second layer where, again, you apply linear transformation followed by a pointwise nonlinearity. You stack a few of these. But observe that these nonlinearities are pointwise. They're really not mixing signal components. Right? So the bulk of the interactions here between different components of your information is being captured with a linear transformation. The nonlinearities sort of like a relatively small tweak that you put on top of that nonlinearity, that linear transformation to make your architecture more expressive. Now that's elementary level machine learning, but if you start working on these architectures, you will pretty soon discover something that is a little bit of a fundamental fact, which is that fully connected neural networks, they do not scale to high dimensional inputs. If you are trying to process an input signal with 20, 30, 50, maybe 100 inputs, a fully connected neural network would do. But if you're trying to process an image with millions of pixels or tens of thousands of pixels, those won't scale. Now, the ones that scale, the ones that attain scalable processing or scalable learning, are those networks that are convolutional. Okay? In the case of image processing, you require the linear transformation that you use at each layer to be an Euclidean convolutional filter. If you don't know what a convolution is, which I doubt that's the case, but anyways, it's just a special type of operation that leverages the translation invariance of image processing. But anyway, so what you have done in order to define this convolutional neural network is you have restricted your linear operations to be convolutions. Now, remember that I told you that the fully connected neural network was not that different from an arbitrary linear transformation. Well, the same applies here, right? So a convolutional neural network is not that different from a convolution. All of your component mixing is being done by the convolutional operation. Your Pointwise nonlinearity is just processing components one at a time. Now, if you want to solve that drone coordination problem that I explained, and this is actually how this video has been constructed, you need to process signals on graphs because the proximity between the agents here, of course, is critical. And in order to process these signals on graphs or to process graphs themselves, you resort to the use of graph convolutional filters. Graph convolutional filters, that is more likely you've never heard of them, but they're not difficult to define. They're just polynomials on a matrix representation of the graph. And the reason why these polynomials are useful is because they attain a level of permutation equivalence. Now, this is the basic introduction to convolutional architectures. Okay, so the reason why Euclidean and graph convolutional filters work is because they leverage signal symmetries. In the case of Euclidean filters, they leverage translation equivariance. In the case of graph filters, they leverage permutation equivariance. Now, the difference between Euclidean and graph filters and Euclidean and graph neural networks is that CNNs and GNNs are better at leveraging quasi-symmetries than Euclideans and graph filters are. And if you want to read about that, these are the two references, which are respectively for the case of CNNs and GNNs. But what has been proven to great success is that convolutional neural networks are more stable to the diffeomorphisms, that is warpings of Euclidean space, and that GNNs, sorry, there's a typo here, are more stable to multiplicative perturbations of the graph. So those extra stability properties imply that CNNs and GNNs, they better exploit quasi-symmetries, and that's the reason why they are preferable to linear filters, even though they are very similar. Now, what is the idea of algebraic neural networks? Well, the idea of algebraic neural networks is to build a level of abstraction on top of CNNs and GNNs. In particular, we want to construct an architecture, or actually the purpose of this talk is to present to you an architecture, which is an algebraic neural network, out of which both CNNs and GNNs can be derived as particular cases. It's not only those, but there are other large number of convolutional architectures like group neural networks or graphon neural networks. You can Google about them. And a large number of unexplored architectures that would fall within that category. So the idea of algebraic neural networks is to have these two, which are pretty important as particular cases, but to be more encompassing than that. That's not the only thing that I want to cover. The fundamental result really that I want to present today is that the shared stability properties of CNNs and GNNs, and I remind you here, I just told you a minute ago that the CNN and the GNN are better at leveraging symmetries than filters are, that shared property is actually a deep consequence of their shared algebraic structure. It's not a coincidence that the CNN outperforms a convolutional filter and that the GNN outperforms a graph filter and that they outperform it in the same way, which is better stability to the formations. That's actually a consequence of the algebraic structure that the CNN and the GNN have, which is an algebraic structure that they inherit from the algebraic neural network. And of course, this holds not only for CNNs and GNNs, it also holds for group, graphon, neural networks. It holds for a large number of architectures that are yet to be explored. Now, this is the introduction to the talk. I am going to get a little mathematical now. There are questions, apparently.
Yeah, can you explain a bit what you meant by the multiplicative deformation of the graph neural network?
Correct. So it's for a multiplicative perturbation of the graph, we mean a perturbation of the graph that you can write as a multiplication with an identity plus a small matrix. It's not an additive. It's not an additive perturbation.
Okay, thank you.
Good. Yeah, these are good questions. So the next question that Fabian would like to ask me is, why do I prefer a multiplicative perturbation relative to an additive perturbation? There are good reasons for that, but I won't get a chance to explain that. It would take me, like a little bit of a big detour, but we can discuss that later. Okay, let me now move on to introduce the notion of algebraic convolutional signal processing, which I will leverage to define algebraic convolutional neural networks. Now, this is quite basic. So if you have an understanding of algebra, I ask that you forgive me because I'm going to really cover like elementary details, but I think that they can be interesting to understand what is the idea behind convolutional processing. Suppose that we are given here a vector space M. Okay, so this is where signals live. So signals are elements of a vector space. So this could be, this could be a vector in Rn. It could be a function in L2, a function defined on a manifold, whatever. Just a vector space. Now, associated to the vector space, so you have a space of endomorphisms. These are the maps that take you from one element in the vector space to another element in the vector space, and that transformation is linear. As I told you, this is very elementary, right? So we're talking about things like matrix multiplications. We are talking about things like linear operators. If you matrix multiplications when your vector space is Rn, linear operations when your vector space is the set of square summable functions in 0, 1, for example. Now, the important point to notice here is the following. So if you want to do linear processing, you need to find a matrix in the space of endomorphisms of M that would be good at processing your data. That's what is not scalable in large numbers of dimensions. If the dimensionality of your vector space is large, then the space of endomorphisms is also potentially large. And that means that learning in that space of endomorphisms is not scalable. You need to search overall matrices, or you need to search overall linear functions. In order to attain a scalable linear signal processing, here is an idea. Let us introduce another algebra. And I say another algebra because the space of endomorphisms is also an algebra. And that algebra will have the purpose of restricting the set of allowable linear maps. And it's going to restrict it to those that are representatives of the elements of the algebra. The representation here is defined by this homomorphism, which maps elements of the algebra A into elements of the endomorphism of M. So filters, convolutional filters, I am going to define them as elements of this algebra. And those elements of the algebra, those filters, are going to operate on signals to produce outputs y, which are given by the application of rho of A to X. This sounds a little unconnected to the definitions of convolutions that I gave a minute ago, but I promise that I'm going to explain the connection in a second. But this is an abstract way of defining convolutional processing. Instead of saying, I will process my signal X with an endomorphism, I am going to process my signal X with an endomorphism, yes, but only among those endomorphisms that can be representatives of an element of another more restrictive algebra. Thus, an algebraic signal processing model is a triplet made up of an algebra A, a vector space M, and a homomorphism rho. The algebra, that's the space where the filters live. And it's meant to define the rules of convolutional signal processing. M is a vector space. That's the simple one. That's the place where your signals live, the elements, the entities that you want to process. And the homomorphism, that's also perhaps the simple one, is just a way of matching the algebra A to the vector space M. It instantiates the filter in the vector space where the signals live. Now, I told you that all of this sounds very complicated because it's meant to be abstract, but it's actually all of it very easy. For example, let's consider the case of graph signal processing. In graph signal processing, the idea is that your signals X live in Rn, and they are associated with the nodes of a graph. So here I have a graph, and different nodes have different values associated with them. There is also a matrix representation of this graph. Convolutional filters in graph signal processing are defined as polynomials on the matrix representation on the graph. And the reason why we like that definition is because that ensures an equivariance to permutations. It ensures the ability of the graph filter to be independent of labeling. Does this definition fit into the framework that I was discussing a minute ago? Well, yes, it does. The signals X live in the vector space made up of vectors of dimension n, it's Rn. Filters are elements of the algebra of polynomials. That is, expressions, right? Symbols that can be written as summations from 0 to k minus 1 of elements of a certain field times a symbol to the power of k. Okay? So the vector space, that's where the signal lives. The algebra, that defines the rules of convolutional processing. I choose an algebra that tells me I am going to restrict attention to operations of this form. In this case, I am going to restrict attention to operations of this form because this is what is going to ensure that my processing is independent of labeling. But I still need to instantiate my abstract filter into my concrete signals. The homomorphism does that. I map my abstract polynomial into a concrete polynomial on the matrix representation of the. Now that's the basic level introduction to algebraic signal processing. I hope it was clear, but perhaps I should go back to resume or to summarize what are the important components. And the important components are these three. It's a triplet made up of an algebra, vector space, and a homomorphism. The algebra defines the rules of operations, like the algebra of polynomials does. The vector space, that's where the signals live. That's the simplest one, perhaps. The homomorphism is not complicated either. It's mapping the algebra, which is an abstract entity, into a concrete set of operations that we can apply to our signal sets. In the case of graph signal processing, these three quantities or these three objects have very clear meanings. The vector space is the space of vectors of dimension n, that's the size of the graph. The filters are elements of the algebra of polynomials, and the homomorphism is just a map from the algebra of polynomials into the space of endomorphisms, which is the space of matrices of size m by n, utilizing the given matrix representation of it. Now, the value, of course, is that this is just one example, but the framework that I introduced is very general. For example, if you want to do graph signal processing on a different graph, you change the vector space to the appropriate graph dimension, you keep the algebra of polynomials, and you replace the homomorphism to the shift operator of the new graph. If instead of that, you want to do discrete time signal processing, you want to process time sequences, the vector space will now be the space of square summable sequences. You still keep the algebra of polynomials, but you replace the homomorphisms to compositions of the translation, the time shift operator. If you want to work with image convolutions, the vector space is now the space of matrices, or given by the dimension of your images. The algebra is the algebra of polynomials of two variables, and the homomorphism contains compositions of horizontals and vertical translation operators. If you want to define group convolutions, the vector space is made up of functions supported on the group. The algebra is the algebra of the group, not unexpectedly, and the homomorphism in this case is just the identity because everything is defined natively in the definition of the group. But you can have what I would like to call whatever convolutions, right? So instead of square summable sequences, you can have square summable functions. You can define functions on manifolds. You can change the fields so that you operate in finite fields. There are interesting applications there. You can change the algebra of polynomials to an algebra of polynomials of multiple variables. You can use a Lie algebra there, although I am not sure that there is any good reason to utilize a Lie algebra, but it's something worth exploring. And the homomorphism is the one that I have to emphasize is not up to be chosen here, right? So the homomorphism is the one that matches the algebra to the vector space. So there's, there is a lot of freedom in exploring the space of the space of signals, and a lot of freedom in exploring the space of filters. But once those two freedoms are taken away from you, the freedom of choosing the homomorphism is, for the most part, taken away from you. Now that concludes my digressions on, or my definitions of algebraic signal processing. I am going to move now to define algebraic neural networks, but this is a good place to stop and ask you if you have any questions.
So in some sense, as soon as I have a symmetry group that I want to be restricted, this restricts sort of the matrices with which the linear transformations in my neural network. So if I can express as a group, then I can sort of this gives me the algebra from the group, and then I can use this to tell me how the maps are restricted.
Excellent. Yes. So like the specific question that Fabian is asking is what's going on with the group here. So yes, exactly what you just said. If you want to have symmetry with respect to a certain group, you say, well, this is the group with which I have to operate. In the particular case of group convolutions, the choice of the group already defines your vector space, and it already defines your algebra, right? So the particular case of group convolutional processing is more restrictive than the previous one. In the case of image processing, the choice of the vector space and the choice of the algebra, they are separate. You could choose, the vector space to be one thing, the algebra to be another thing. In the case of group processing, they're tied, which is the reason why the homomorphism is the identity.
Yeah. Thank you.
Hi, professors. I was wondering the GNN is generally more stable than the CNN in many cases.
You were wondering the GNN is more stable than the CNN.
Yes, in many cases, yes.
Yeah, okay. So the CNN and the GNN, they are used to process different type of information, right? So the CNN is used to process images or signals in time. It's used to process information that has a Euclidean structure. The GNN is used to process signals that have graph structure. So in a sense, they are applied to different types of information, right? So what I meant to say, if you're asking me about the slide that I had before, is that the convolutional neural networks or the graph neural networks, they're more stable than the respective convolutional filters or graph filters.
Oh, okay. So if we consider a network with multiple nodes and each node has its geometric information, so I was wondering, this is the information that can be better processed by a GNA instead of a CNA?
Yes, if you have information that is supported in a graph, you should process that with a GNN instead of a CNN, indeed.
Oh, okay. Thank you very much.
Thank you.
Okay.
Okay, so I have defined the algebraic filters. I now need to define the algebraic neural networks. This is actually quite beautiful because once you have defined your filters, defining neural networks is very easy. So I am illustrating here how a layer of an algebraic neural network is going to look like. So in each layer, you have a specific ASP model, which is defined by a certain algebra, a certain vector space, and a certain homomorphism. That specifies the type of convolutional processing. Within each layer, you add a pointwise nonlinearity, and you add a pooling operator here, which I'm going to explain in a minute. So I am composing convolutional filters with pointwise nonlinearities. This pooling operator here serves the purpose of matching the vector space of layer L to the vector space of layer L plus 1. If you know what pooling does, this is literally what it is, right? So you have an image and you pool pixels to construct an image of a smaller dimensionality. So that means that when you transition from layer L to layer L plus 1, you need to map one vector space into the other. The pooling operation is the one that performs that matching of different vector spaces. Now, I should emphasize here that theoretically, the trainable parameters are the filters H of L. But of course, we don't train on H of L numerically. We train directly on the homomorphism, rho L of H sub L. Once you have individual layers, you stack them on top of each other, and that's the definition of the algebraic neural network. And since convolutional neural networks, graph neural networks, group neural networks, whatever neural networks will follow as particular cases of this algebraic neural network because of the simple fact that these algebraic filters that I am utilizing at each layer are general cases or general abstractions of convolutional filters, graph filters, group filters, whatever. Now that concludes the basic part of the talk in which I wanted to talk about architectures. In the next half of the talk, I am going to talk about deformations, stability, and frequency representations. So this is going to get a little heavier, so just a warning about that. There's someone raising his hand here, Chase, I believe.
Hi, yeah, so on the previous slide, you indicate that you have some freedom to choose different algebras for each layer, but is there, does one do that in practice? Like for instance, if you have convolutional layer after convolutional layer after convolutional layer, like what does it mean to mix the algebra?
Of course, yes. Chase here is asking me the question. I mean, do you really want the flexibility of choosing the algebra, right? So there's maybe a difference between defining an object that I can study mathematically, and then utilizing that object in practice. In general, I don't see much reason to utilize different algebras or different vector spaces or different layers. Although I gotta tell you that there is some work on doing image processing that is invariant to both translations and rotations. So in those cases, you utilize some filters that are invariant to translations, then you utilize some other filters that are invariant to rotations. So that will be captured with a change of both the vector space and the algebra.
Thanks. Yeah, I guess you could, maybe it would also make sense to use subalgebras as you go to further and further layers in the network.
Yeah, would be. Yeah.
Hi, sorry, can I make a quick question?
Yes, of course.
So two slides, if you go to slides 32, I guess, no, maybe 33 then. Yeah, so just a quick, can you give me a quick comment on what does it mean that we train directly, let's say on the homomorphism, like raw L, HL, and we don't train directly on the filter parameters?
Sure. Yeah. Well, like the trainable parameters in this architecture, as it is defined, are the filters which live in this abstract algebra. Those objects are symbols, right? I mean, they're not necessarily numbers. So in order to train numerically, you apply the endomorphism that gives you an endomorph. That gives you the map of the abstract filter into concrete filters. You train those. Like in the case of GSP, for example, you train the filter coefficients HK in this expression. You don't train the filters HK in this other expression. This is just a symbol that you write on a piece of paper.
Yeah, but okay, but because the filter itself contains also the S, so I mean, we just learned the H coefficients, not also the matrix itself. Let's say.
Correct. Yeah. Mathematically, this is equivalent because it's an endomorphism, so you can go from one to the other. But in practice, you operate with a second.
Okay, thank you.
Okay, so we have another question by Pim.
Hey, thanks. I have a question about this decomposition between an endomorphism followed by a pooling operation. For example, if you would map linearly from like one channel to 3 channels, I don't really see how we can see this as like one parameterized endomorphism followed by a pooling operation.
Very good. So the question that you're asking me is a little different. It has to be with the fact that I am describing an architecture in which each layer is made up of a single filter. In reality, you have multiple channels on which you operate with multiple filters. We can describe that, but the description gets cumbersome, and it's in the paper, but it's not in the slides.
Okay, thank you.
Okay. Thanks a lot for the questions. I'm running late because of them, but that's a good reason to be running late. Let me talk about the formations. Okay, so there is something important here, which is that the algebraic models determines the equivariance properties of the algebraic neural network. That's what makes convolutional processing useful. Equivariant to translations in CNNs, equivariant to permutations in GNNs, equivariance to actions of the group in the case of group neural networks. Now, the thing is these are all properties of the filters. These are properties that the filters has and that the algebraic neural network inherit. Now, in practice, and there's no question about this, neural networks outperform algebraic filters. So a good question here is why? And well, there are probably several reasons why, but I'm going to give you at least one, which is that neural networks or algebraic neural networks have better stability to deformations. In order to do that, I need to introduce a couple of objects, which are the notion of the generator of the algebra and the notion of a shift operator. The generator of an algebra is, what its name indicates, is a subset of elements of the algebra that generate all of the other elements of the algebra as polynomial functions of elements of G. The shift operator is defined as the set of homomorphism images of the set of generators. For each generator that you have, you compute the image through the action of the homomorphism, and that you call a shift operator. The reason why these definitions in terms of generators and shift operators are useful is because they allow us to write filters as polynomials on shift operators. This is a little insidious because it's independent of the fact of whether we are utilizing the algebra of polynomials or not. Okay, so you can always, for whatever algebra, write down your filters as polynomials on the shift operators. Once you construct this, we are going to choose to define perturbations of algebraic models as perturbations of the shift operators, which are given by a certain perturbation function T of S, which I am going to define in a second. When we perturb the shift operator, the algebraic signal processing model is perturbed to one in which the homomorphism is a little different. Because instead of writing polynomials on the shift operators, we write polynomials on the deformed shift operator. The polynomials that define the filters are the same. I didn't change the algebra. The underlying algebra that I am using is still the same. But we are using a perturbation of the shift operator. Now, this is a peculiar way for me to choose to define a perturbation, but it is actually well motivated. For example, in the case of graphs, the shift operator represents the graph itself. So the perturbation that I am defining here, it just means that I am operating on a different graph. In the case of times, S is a representation of the translation operator. It's encoding translation equivariance. S tilde, therefore, is a representation of quasi-translation equivariance. So the modifications of the shift operator that I have defined here, they introduce modifications in the symmetries that we are trying to capture. Instead of capturing perfect symmetries, we are trying to capture near symmetries. In order to present the stability theorem, there's a couple of more definitions that I need to introduce. The first one is that we have been unable to understand arbitrary perturbations, so we have restricted our analysis to the case of linear plus multiplicative perturbations. Both of the perturbation operators here are assumed to be compact with sub-unit norms. And I should point out that the perturbation operators and the shift operators, they don't need to commute. I am going to therefore define a commutation factor to measure how far from commutative the perturbation and the shift operator are. Given these assumptions, we can define the notion of stability to deformations, and we can prove that our algebraic filters are indeed stable to deformations. Now, in order to define an stable operator, this is the definition that I am going to adopt. We are going to require that we are stable to the magnitude of the perturbation, and that we are also stable to the rate of change of the perturbation. This second restriction here is important. Suppose that you are warping Euclidean space. You not only want the warping to be small, you want the rate at which the warping changes to be small. If you are perturbing a graph, you want the modifications of your edges to be small, but you also want similar edges to be modified by similar amounts. You don't want a graph to be changed, if two different edges are one, you don't want one of them to be perturbed by 0.1 and another one being perturbed by 1. You want them to be perturbed by similar amounts. Now, if we have a perturbation of our operator that is bounded by the sum of these two quantities, we are going to say that our operator is stable. Something important is that stability is not a given. It's easy to construct counterexamples in both CNNs and GNNs in which you will have unstable operators, okay? In order to have stable operators, I need to introduce two restrictions, which are that my filters be Lipschitz and that my filters be integral Lipschitz. That the filters are Lipschitz means that they are Lipschitz. That they are integral Lipschitz means that their derivatives are sorry, their integrals are Lipschitz. There is the product of lambda with the derivative of the filter is bounded by a certain quantity. There is one small detail in these definitions, which is I am defining polynomials on the field on which the algebraic filter is defined. The reason for that is because my filters are polynomials on shift operators. They are therefore isomorphic to polynomials with complex variables if you feel these the reals, or they are isomorphic to polynomials on the algebraic closure of the field in which you operate. So let me repeat the quantities that I defined. Okay, I defined stability as the possibility or the ability of my operator, the property of my operator, being bounded by a constant quantity multiplying the size of the perturbation plus another constant quantity multiplying the rate of change of the perturbation. Not all filters are going to be stable. In order for me to claim stability of filters, I need to introduce a restriction that they be Lipschitz and the restriction that they be integral Lipschitz. And these conditions are expressed over the field on which the filters are defined, which I can do because filters and polynomials over the field are isomorphic objects. If filters are Lipschitz and integral Lipschitz, they are stable. They can be proven to be stable with respect to the perturbations of the graph. Perturbations of the shift operator, in the sense that the perturbation of the output of the filter is bounded by a quantity that depends on the value, on the size of the perturbation, and another quantity that depends on the Frechet derivative of the perturbation of the shift operator. There's a couple of things that I want to point out. The first one here is we have this commutativity factor, which defines, how far from commuting with each other the perturbation and the shift operator are. This commutativity constant is bounded, and it affects the stability constant, but it doesn't generate instability. So that's important to point out. The other important observation is this one. So given that our filters are integral Lipschitz, they are either stable or they are discriminative. They cannot be stable and discriminative at the same time. And observe what happens, right? Because this condition here requires that your filter be constant for some values of lambda. The product of lambda with the derivative is bounded, which means that the derivative is inversely proportional to lambda, which means that as you increase lambda, the filter becomes less discriminative. This is related with the notion of frequency responses, and I am going to go and cover that in a minute. So it will become more clear when I do that. Now, the point that you should be asking this is, okay, are algebraic neural networks stable? And the answer is yes, of course. Algebraic neural networks are also stable. Oh, sorry, that's a question.
Yeah, can you go back to the previous slide? So
Yes.
Can you say something about the converse? When is is every stable filter Lipschitz and integral Lipschitz, or?
Oh, that's a very good question. So I am saying here, if the filter is Lipschitz and integral Lipschitz, I am saying that it is stable. So the question that you're asking me is, what happens if I violate these conditions?
Yeah.
So if you violate these conditions, you can find filters that are going to be unstable, but that's not quite a converse, right? So this is not an if and only if condition.
Yeah. My question is,
there could be a tighter condition that I don't know. We don't have a converse for this theorem.
okay, thank you.
Yes, that's a very good question. I had never thought of that. So we don't have a converse. We can have counterexamples of filters that don't satisfy this condition, and they are unstable. But there could be another condition that is tighter than the one that we have here.
So I have a question. So if we want to ensure that the filter is stable, so is that we need to ensure that the filter is Lipschitz or integral Lipschitz?
So I didn't understand the last thing that you said. Do we need to ensure?
So can you go back to the last slide? Yes, I think it's 43. Yes. So yes. So it said that the filter is Lipschitz and integral Lipschitz, that it can be stable. So in another word, I was wondering if we want to make sure that the filter is stable, we need to design a filter that is Lipschitz or integral Lipschitz, or the filter is unlikely to be stable.
Okay, so I think that your question is more or less the same question that Fabian just asked, right? So the theorems are a sufficient condition. If the filter is Lipschitz and integral Lipschitz, it will be stable, but there could be a condition that is tighter than that I don't know, that will make the filters stable as well.
Okay, thank
you. I do know that there are filters that don't satisfy these conditions that are unstable, but I can't tell you that it is an if and only if condition.
Okay. Thank you.
Okay. Now the last topic that I want to cover is, because like all of this sounds mysterious, perhaps, or the stability sounds a little mysterious. I wanted to actually tell you that the stability results here are not that surprising, because it all depends or hinges upon the frequency representations of these algebraic filters. The filter is defined as a polynomial on the generators, which means that I can define this isomorphic quantity, which is a polynomial on the field on which the vector space lives. That isomorphic entity is a polynomial of whatever number of variables, but let's just look at the case in which we have a single generator. If you have a single generator, this frequency representation is just a polynomial. I mean, just a function of one variable. It will be real or complex, but let's just even make it simple. Let's suppose that it's a function of just a single real value. What is very beautiful about this frequency representation is that it decouples the filter from the homomorphism completely. Right? It decouples the filter from the shift operator that specifies actions on X. So remember that we have our abstract algebra where the filters are defined, and then we make them into concrete instantiations. Actually, we have another mapping here, which is into the frequency representation. And that frequency representation is independent of the specific instantiation of the filter on the vector space. Now, what is the role of that instantiation? The role of that instantiation is to specify the eigenvalues that a particular homomorphism ends up observing. And so the shift operator, the mapping between the generators of the algebra to the space of endomorphisms is through a set of shift operators. So actually only one in this particular case, because I am looking at a problem with a single generator. But shift operator will have some eigenvalues on that vector space. Those eigenvalues are the ones that define the effect of the endomorphism on a particular filter by instantiating them. The shift operator S instantiates those blue eigenvalues here. the shift operators hat instantiates these other eigenvalues. So in those theorems, this is the core of that analysis, is understanding what happens when these eigenvalues move. And I cannot prove the theorem here. It would take me a couple hours to do that, but I can give you the intuition of why the theorem is true by explaining to you the effect of dilations. When you consider a dilation of your shift operator, the eigenvalues dilate. And observe that this dilation of eigenvalues means that eigenvalues close to zero, they move less than eigenvalues that are far away from zero. That's the reason why we have this integral Lipschitz constant, because the farther away we are from the origin, the more that a filter can be perturbed, because the eigenvalues can change by a larger amount. What I mean is this: if we are operating on the blue shift operator, this is the value that we think we are instantiating. But in reality, we are instantiating the filter at the dilated eigenvalue. Now, if we are close to zero, this movement is small. But if we are far away from zero, the movement is large. And then the change in the value of the filter that we instantiate can be significant. In order to avoid that, we introduce the integral Lipschitz condition. And that integral Lipschitz condition will prevent the filter from moving. Thus, at low frequencies, the eigenvalues don't move, and we therefore have stability. At high frequencies, the eigenvalues move, but the filter does not. Therefore, we still have stability. But what is the cost of that? The cost of that is discriminability, of course. At low frequencies, you can design these sharp filters that will isolate your features. At medium frequencies, you sort of can, but at large frequencies, you cannot design these sharp, highly discriminative filters. You need to restrict them to the integral Lipschitz for them to be stable. This is where the nonlinearity comes into play, because the nonlinearity is like a demodulator operator, which is going to move your high frequency components into low frequencies where you can discriminate them with a stable field. Now, these last 5 or 6 slides where I am explaining the perturbation in the frequency domain, this is literally a translation of the results that exist for convolutional neural networks. It is also literally a translation of results that exist for graph neural networks. But it is very important to remark that this abstract analysis shows you that the stability properties of CNNs and GNNs, they're literally identical. And they come just from the fact that both the CNN and the GNN are relying on convolutional filters that have an identical algebraic structure. And of course, it also means that these results hold for group neural networks, graphon neural networks, whatever neural networks that have a convolutional structure. This is the end of the talk, so this is the message. Algebraic neural networks can be simultaneously discriminative and stable to deformations, but algebraic filters cannot. Or if you get me on a more honest day, it's not that one is stable and the other is not. Is that for the same sensitivity, algebraic neural networks are more discriminative than algebraic filters. And this is the end of the talk. I just have some closing comments here. So this is what I think is exciting about this topic, which is that it provides a common language for convolutional, graph, graphon, group, whatever neural networks. This tool has also uncovered a shared stability versus discriminability trade-off that stems from a shared algebraic structure. And that trade-off is the following. Algebraic linear filters are either stable or discriminative, but they can be both. Algebraic neural networks, on the other hand, they can be both stable and discriminative because of the demodulation that is performed by the pointwise nonlinearity. I think there's quite a lot of research that can be done in this area. My personal theory wish list includes extensions to non-commutative algebras. It also includes extensions to Banach algebras. My application wish list includes Lie algebras, convolutions on manifolds, convolutions on Markov random fields. This is the end of my talk. If you thought that this was interesting, this is the paper where these results have been reported. You can also check my course on graph neural networks. Lecture 12 in particular is about algebraic neural networks. And if you have questions or ideas, myself and the other Alejandro will be very happy to get an email from you. Thanks for listening, and I really appreciate that you have taken your time to be here today. Thank you.
All right, thank you very much, Alejandro. We can thank him with this clap emojis. I'll clap for all of us.
Thank you.
We already had quite a few questions, but we have time for some more. While people are thinking about this, I'll start with one question. Can you say a few words on adversarial attacks? So we know that sort of you can change the prediction of a neural network by changing a few pixels, and then it thinks it's a monkey instead of a banana or whatever. So which condition is violated in these adversarial attacks?
Very good, very good. So the question is, what happens with an adversarial attack? So the adversarial attack is violating both conditions on the size of the deformation, right? Like in the adversarial attack, you get an individual pixel and you change it by a completely different value. When you do that, both the size of the perturbation and the rate of change of the perturbation are very significant. Make sense? Right? Because the absolute value of the perturbation is large, and it's also very different from whatever it is that you're doing around your nearby pixels. Actually, if you care about this type of adversarial attacks, there's actually a much simpler explanation for that. These adversarial attacks are very high frequency components, right? Because of like a spike that you put in the middle of the image. It's like adding a delta function. And this analysis tells you that these high frequencies are the things that are difficult to capture with your convolutional filters. So at the end of the day, this is the reason why these adversarial attacks work, because they're very high frequency attacks, and very, very high frequencies are the ones that any convolutional filter will have trouble processing.
Yeah, but I mean, maybe this goes back to my converse question, but if I change just any pixel to any value, this typically is not an adversarial attack. So I can sort of change some pixel and the neural network will not change its answer, but then I change a different pixel and all of a sudden it changes, and it's also high frequency and the rate of change is also very large.
Yeah, it's a very good point. Yeah. Like, the point is, there are high frequencies and there are other high frequencies, right? So yeah, you need to find those high frequencies that are relevant. But I'm starting to talk gibberish, so I'm gonna stop here before I get myself in trouble.
Thank you.
Yeah, there's one more thing, Fabian, that I could say to that extent, which is that if you want to take care of this type of adversarial attacks, what you have to do is actually very simple. You need to begin by pre-filtering your signal, right? You just send it through a low-pass filter, and you eliminate those other pixels. But of course, this is an arms race. I mean, if I put a low-pass filter, then you will find another way of creating trouble for me.
Yeah, of course, and as I said, you have this trade-off of making your network less discriminable. So
exactly, yeah. That I think is a very good point, which follows from this type of analysis too, right? I mean, the more discriminative that you make your network, the more sensitive that you make it to perturb.
Thank you.
Hi, professors. We know that the input of GNA is always a graph with a adjacency matrix. So we know that the adjacency matrix contains the edge and the vertex, which is means nodes. So I was wondering how these nodes interact with the graph filter in the GNA's basic computation. For example, we can take the GCA as an example. Thank you very much. I just know the mathematical expression, but I still have some puzzle about its physical meaning. Thanks.
Okay, I can try to explain that.
Okay.
Is that I don't really have the equations to explain that, but I will try nevertheless. So like if you see this expression here, it's a polynomial on the matrix representations on the graph, right? So this is like an adjacency matrix.
Yes.
So if you get this sum over here, which is a matrix, no, sorry, not the sum. If you get the product S times X, which is just a matrix vector multiplication.
Yes.
That S is the adjacency matrix of the graph. So it's a sparse matrix with only a few non-zero entries.
Yes.
Okay, so
I
when you do the product S times X, you are doing an average of the values of your neighbors. Right? So when when you're at node 1 and you look at the product of SX evaluated at node 1, it will depend only on the value at node 2 and the value at node 3. Make sense?
Oh, I see. Yes, it may say so. It compute based on its neighborhood. Yes.
Based on its neighbors. So that's the locality of the operator. Actually, maybe the reason why it's permutation equivariant, which is that the operations that you are making, they depend only on the values of your neighbors. You define the GCN, right? I mean, the GCN, it's the same formula, except that in the case of the GCN, people prefer to write it in expanded form instead of writing it using matrix notation.
Yes,
okay?
yes, thank you. Yes, yeah, thank you.
Chase?
Hi, yeah, thanks again for a very nice talk. I had a question about a comment that you made earlier on about there being essentially your choice of homomorphisms are fixed once you specify an algebra and a vector space. I mean, obviously, you're not claiming that it's unique because you have always a trivial homomorphism or something. So what is the criteria? Like, presumably you're implying there's only one or a very limited number of interesting ones. Can you speak about what it is that you're basing that on?
Yes. Chase is asking me about this slide precisely, where I am saying that the homomorphism has to be chosen to match the algebra to the vector space. There's not only one way of doing that, and there could be several that are interesting. So what I meant to say is that, and I perhaps didn't say it correctly, but what I mean is this: when you choose the vector space and the algebra, the choice of homomorphism gets restricted because you have to match the algebra to the vector space. So that's all I wanted to say. In some cases, that restriction is very significant. For example, if you're doing group convolutions, you have to restrict the homomorphism to be the identity. There's no other one that would work here. But if you are working with graph signal processing, you still have quite a lot of freedom in the selection of the homomorphism, because any homomorphism of this form for any matrix would work. Make sense, Chase?
Yeah, but do you think there are interesting implications for like
it depends? Yes. Okay. So it depends on the specific application. If you are working with graph signal processing, then every graph is characterized by the same algebra, the same vector. Assuming that the graphs have the same number of nodes, the same vector space, it's just that they are utilizing different homomorphisms.
I see. Thanks.
No? But if you're looking at group signal processing, that's the complete opposite. There's only one homomorphism that would work. If you are looking at things like discrete time signal processing, here there are several possible homomorphisms, but there's only one that is interested in practice. But that's different from the case of groups, right? I mean, in the case of groups, there's only one that works in theory. In the case of time, the only one that makes sense, given the structure of the signal, is the translation operator. So there's three possibilities, right? So you have quite a lot of freedom, like in graph signal processing. You have theoretical restrictions, like in group signal processing, or you have practical restrictions, like in discrete time signal processing.
Okay, are there further questions? I can't see any, so I'd say we all thank Alejandro again for his very nice talk.
Yeah. So thank you, everyone. If you have any questions, please, shoot me an email. Happy to respond.
And we hopefully see all of you in 2 weeks. Thank you, everyone. Bye.